Hi, Professor Kilolea. So to begin our discussion of molecular orbital theory, I wanted to go over some quick fundamentals, which this theory is essentially based upon. So we have the Bohr model, in which there is a negatively charged electron orbiting around a positively charged nucleus. And we have the centripetal force being equal to the Coulombic attraction between these charged particles, and also a centrifugal force, which is equal and opposite to the centripetal force. We have a quantized angular momentum, which is set equal to nh bar, and a quantized circumference of the orbit, which is an integer number of wavelengths such that the electron will not constructively or destructively interfere with itself. If we solve for v in this equation and plug it into this one, we get the Bohr radii and find the derivation for the Rydberg constant. And furthermore, we get into this familiar idea that the total energy is the sum of the kinetic and potential energies. When we have a negative total energy, that refers to an electron in a bound state. So here we could look at it in this depiction, where the electron is in a potential well and needs energy to be provided to it in order to be freed from this potential well. The energy which frees an electron from its orbit is known as the ionization energy. So again, if we look at this basic idea here, we have the electron energy approaching zero as it's promoted from energy level to energy level, and it also becomes more and more distant from the nucleus as it gains more energy. And furthermore, if its energy does become zero or greater than zero, that would refer to an electron in an unbound state. Okay, so let's get into our hydrogenic atoms and their wave functions. So we have the Hamiltonian operator, which we quickly simplify thanks to the Born-Oppenheimer approximation, in which we say that the mass of the nucleus is so much greater than the mass of the electron that we just essentially treat the nucleus as if it's stationary, and then we only worry about the motion of the electron relative to the nucleus. And that is depicted here in this equation. So, furthermore, our wave functions that result from this operator are all in terms of spherical coordinates. So we have this wave function, which then we can separate into an angular and radial wave function. So here we can deal with the angular wave function through spherical harmonics, and then that just leaves us with our radial equation. So here we have the effective potential energy in this radial equation, and we know that the Coulombic attraction is proportional to 1 over r, and the centrifugal force is proportional to 1 over r squared. Like we said earlier, the centrifugal force pushes the electron away from the nucleus, and the Coulombic attraction pushes the electron toward the nucleus. So the Coulombic attraction predominates when the electron is very distant from the nucleus. So we put in this exponential term, so it decays, and this radial equation becomes zero as rho becomes infinite, because there is a very low probability of finding an electron infinitely far away from the nucleus if that electron is still bound. So in the case of the centrifugal force, we raise rho to the power of the angular momentum such that when we're very close to the nucleus, when rho is a very small number, again, our radial equation will become zero, because this force will be very strong and will push the electron away from the nucleus. So we don't want that probability to be high there. We want it to be low. And then also, if there is no angular momentum, we want this term to essentially disappear, which it does, and then we only have Coulombic attraction. And then we also have N, L, and ML. Obviously, N gives us the energy, L gives us the magnitude of the angular momentum, and ML gives us the orientation of the angular momentum. And then we just have our shells and our subshells given this certain type of naming with letters rather than numbers, which isn't confusing at all. And then we move on to atomic orbitals. So we'll start with s orbitals, which are spherically symmetric. So we look at the number of radial nodes, which is equal to n minus 1, and we see that the total nodes in an orbital wave function is going to be n minus 1 minus L. So then if we take a cross-section of our spherically symmetric s orbital, we'd kind of see it as having electron density, and then a radial node, and then electron density, and then a radial node, and so on and so forth. And we have the wave function for a 1s electron right here, which has no radial nodes, obviously because 1 minus 1 is 0. So we'll move on to p orbitals, where we have n equals 2, l equals 0 and 1, and ml equals plus or minus 1 and 0. We have the pz orbital, and this naming is basically just because z is equal to r cosine theta in spherical coordinates, and then we have it multiplied by the radial function. Furthermore, we have each orbital just basically residing with respect to its axis with a node in the plane between it here. So, and all these originate from linear combinations, as we discussed here, and I just really wanted to put a quick note that a superposition is a linear combination, and it essentially just mixes the characteristics of multiple descriptions of one thing, and that's a really essential idea to what we're doing, and that's where we see all these orbital descriptions come from. The same goes for the d orbitals as well, and I have a little photo to accompany the presentation, if you give me 1 second here. So we see the geometry of the d orbitals is given right here, and there's 5 linear combinations which we can create to give ourselves the d orbitals. Okay, so then if we look at the orbitals of many electron atoms, our difficulties start to originate in the fact that these electrons have electrostatic repulsion. They interact, and it's really hard to make these calculations, so we just do approximation. We totally ignore these repulsions, and we just combine these hydrogenic wave functions such that we just multiply them together and then apply our Hamiltonian in a way that gives us the energy of the first plus the energy of the second, and then we get our separated wave function, which is equivalent to this wave function of both R1 and R2. And here, R1 and R2 is just 2 electrons in 2 different orbitals. And so that kind of gives us an idea of where we start to approximate, other than the, obviously, the Born-Oppenheimer approximation. So moving on from there, we look at the characteristics of electrons and configurations. And I just wanted to make a really quick note about the symmetric and antisymmetric spatial wave functions. And a really important note is that the antisymmetric spatial wave function vanishes when R1 is equal to R2. And again, here we're looking at a linear combination for 2 electrons in 2 different orbitals, and we can't distinguish between the electrons or which orbitals the electrons are in, so that's why we need to make this linear combination. And then furthermore, I think that a really fine point here is we also have like a spin wave function, which is given by S and ms, and this kind of correlates to L, being spin being the intrinsic angular momentum of a particle, and this kind of correlates to ml, like I was saying. And then an important factor that we have to deal with here is the Pauli principle, which basically says the wave function must change when the label of the 2 electrons are interchanged. So essentially we need this to happen. We need the wave function to become negative when we interchange the labels on these 2 particles. So how does this all combine in with spin and the spatial wave equation? So basically we can have spin up or spin down. Alpha means spin up, beta means spin down. So this gives us 4 possible combinations. We can have both up, both down, or we can have this symmetric linear combination, or we can have this anti-symmetric linear combination. So to make this a little bit easier, basically all of these 3 are all thought of as symmetric, and the symmetric ones are basically equivalent to the 2 electrons having the same spin, right? So the spins are parallel and they don't cancel out. So to satisfy the Pauli principle, we have to realize that when we create a full wave function with of both spatial and spin wave functions, we can only combine the symmetric spatial wave function with the antisymmetric spin wave function, because we need to satisfy the Pauli principle. So what's really important here, something that I realized, and it's again just like a fine point that really kind of helped me understand what was going on later on, is that, well, because the antisymmetric wave function vanishes when R1 equals R2, that means that these electrons cannot be at the same point. So this means that basically with the antisymmetric wave function, you can't have electrons occupying the same space, so that immediately means that these electrons are separate. Well, with the antisymmetric wave equation, we can only combine it with the symmetric spin wave functions or wave equations, right? So this means that when our electrons are separate, which is given by the antisymmetric, that means that our spins are parallel. And furthermore, this means that for this spatial wave equation, this means that the electrons can be together. They can occupy the same spot, right? And that means that we have to use the antisymmetric spin wave function. And this means that the spins are anti-parallel, or opposite. So when we're looking at this, this kind of gives us the idea of why we have to pair electrons with opposite spins, because when they can occupy the same space, they must be multiplied by the antisymmetric linear combination in order to satisfy the Pauli principle. And from that, you get the Pauli exclusion principle, right? Because this is necessarily the way that the electrons are going to pair based off of the combination of the spatial wave function and the spin wave function. And then also we see the origin of triplet and singlet terms is because is really the same reason, is because when we have the antisymmetric, we can have 3 different symmetric spin wave functions. And furthermore, this is why the triplet is lower in energy than the singlet, is because when we have the triplet, we're using the antisymmetric wave function. And with the antisymmetric wave function, we can't have the electrons in the same exact spot. And when we can't have the electrons in the same exact spot, that necessarily means that we're going to reduce repulsion, which is going to lower energy, because repulsion increases energy. So we'll move on and we'll go to just a really quick thing about building orbitals that I thought was important. And we've got the idea of shielding, which basically means that the electrons will repel each other within a certain radial distance of a given electron. So the effect here is that the actual nuclear charge is reduced for this electron, but is not so much reduced for, say, this electron. So if we thought about this electron rotating around, we'd see that both of these electrons here are in a given radius. So this means that they will have repulsive qualities. And also, just because of this radial distance being lower for these 2 electrons, it means that it will more easily interact with the positive charge on the nucleus. Also, something important here about building orbitals is penetration. So we want to look at the radial probability, or the radial distributions here. So if we look at the radial distribution for a 2s, we see that the maximum amplitude is actually further away from the nucleus than the 2p. But we have this little area of non-zero probability, which means that this 2s can actually penetrate into the space that we would kind of designate for the 1s. So this penetration actually moves the overall average distance of the 2s closer to the nucleus than the 2p. And furthermore, we just have a couple other things that pop up here that are really kind of just dictated by electron repulsion. So obviously we have electrons occupy orbitals in such a way that energy is minimized. So the reason that they fill singly first, and that they adopt the configuration with the greatest number of unpaired electrons, is to minimize electron repulsion. And again, the reason why we fill 4s before 3d is actually the same reason, is because when we fill 4s, we can get their spins to cancel. But if we fill singly in 3d, we have these parallel electrons, and they will repel. And then furthermore, we have the selection rules, and this is just really based off the conservation of angular momentum. And we know that the intrinsic value of angular momentum for a photon is equal to 1. So therefore, the photon can either add or carry away a value of 1 angular momentum. And therefore, because it is conserved, we can only change the value of L for our electron by plus or minus 1. And then also we have the fine structure of atoms, which just essentially says that the spin, the intrinsic angular momentums can either match up or essentially not. They can be opposite or they can be equal to the spins of the orbital angular momentum, right? So we get high energy in this situation, where they're opposite, and low energy where they correlate here. So you can see I and S are opposite. And so those are the other findings from that bit. So getting into the heart of the topic now, hopefully I haven't spent too much time, we have valence bond theory and molecular orbital theory. So in valence bond theory, we obviously have another linear combination of two atomic orbitals. And the main difference here is the localized bond approach of the valence bond theory, where we just have these two atomic orbitals overlapping, which causes the bond, but we're not necessarily making a new molecular orbital, right? And again, we have this constructive interference, which the increased electron density. We have two wave functions, two unpaired electrons. Furthermore, a big part of valence bond theory is we have resonance, which essentially just means, again, that we have superpositions of multiple different wave functions when we're considering maybe a covalent versus an ionic. Obviously, we draw resonance structures in the same way. We determine this parameter using the variation principle, which we'll talk about later. And yeah, so we're representing different electron distributions with the same nuclear framework. Also, something that is in valence bond theory but is not found in molecular orbital theory is the idea of promotion and furthermore hybridization. Right? So in valence bond theory, we think of constructive and destructive interference create four new orbitals, which are degenerate. And then the lone pairs just contribute to the shape, which is another problem because then that doesn't really explain the paramagnetic nature of O2. And we can, in the hybridization scheme, we also can leave some orbitals alone, like p orbitals, so they can overlap and make pi bonds. So anyway, we're going to look at molecular orbital theory and more differences between the two. So we have atomic orbitals combined to form molecular orbitals. There's no hybridization. And bonds are localized throughout the entire molecule rather than just two atoms. Furthermore, we're going to mix atomic orbitals, and for every atomic orbital we mix, we're going to get a molecular orbital, which results in bonding and anti-bonding. There's no need to worry about resonance because electrons are always delocalized. And again, when we have these unpaired electrons, we know that they will essentially contribute some magnetic character because they align with the magnetic field. And MO theory does describe that accurately. So in the case of molecular orbitals, we use linear combinations of atomic orbitals, and we consider all of the valence electrons, and we say that they take part in the creation of these molecular orbitals. Furthermore, we just have a brief description here. Obviously, the overlap of a 1s creates bonding and anti-bonding here. with them being in phase. Obviously, these are all rough pictures just to give you the gist of what's going on. So we have the 1 sigma, and then this essentially means the Gerade, I could never pronounce it correctly, an Ungerade. Basically is just talking about the symmetry of the bond, and if it's the same on either side, if you go back and forth like so. So you just want plus and plus anyway. So in the case of sigma bonds, we want them to be symmetrical or the same on their inversion symmetry. And then we get a bonding and anti-bonding. With the 2s, it's really the same story. These two combine to become one molecular orbital, and then we have this delocalization where the electron can exist anywhere in there. And then we also have our anti-bonding, which we give it the star, and the Ungerade, which again is just mean it's anti-symmetric upon inversion. And then we have 2pz and 2p, which 2pz again combines to form a sigma bond, and again bonding, anti-bonding. And then here we have the 2 degenerate pi molecular orbitals, and they actually have reverse symmetry just by the way that they come together. So then we know that basically the anti-symmetrical one contributes to bonding, or sorry, yes, the asymmetrical one upon inversion contributes to bonding, and the symmetrical version contributes to anti-bonding. So furthermore, if we get into MO theory, we know that they come from linear combinations. So if we're looking at the H2 molecular ion, we're basically looking at this region from the bonding, at least, from the bonding orbital of increased electron density between these two, right? And if we look at our Hamiltonian, again, we have the same type of setup for the motion of the electron relative to the nucleus. Our difference really comes here when we have the attraction between the nuclei and then the repulsion between the nuclei, which I showed here. So these nuclei will definitely repel each other. So then we have the linear combination and the probability density amplitude given in the bonding orbital, which is proportional to this, where you add 2 times the multiplication of wave function A and B, and then the anti-bonding orbital linear combination, the probability density function, again, is proportional to this, where we're subtracting it. And the reason for the anti-bonding orbital and the reason it's in higher energy is because we're looking at an electron that is really avoiding the internuclear region, which gets back to the heart of what I was saying earlier, because this anti-symmetrical wave function doesn't really allow for R1 to equal R2, right? When R1 equals R2, or the electrons are in the same place, you get 0, right? Well, that creates a node, right? So we'd look at this, if I wanted to designate it pictorially really quick, we would have something like so, and a node right here. And this is higher energy because, well, there's no electrons occupying this intermolecular region. I drew the electron up here, just not in the intermolecular region. And basically, you have a node at the midpoint, and that's because if they were both in the same position, the wave function would be equal to 0. And with our higher energy, without electrons occupying this intermolecular region, we have more repulsion between the nuclei. And anyway, once we move on to homonuclear diatomics, we obviously see the generic MO bonding kind of depiction where we have 2 electrons occupying the bonding orbital and then none in the anti-bonding orbital. And we use bond order to describe the strength and the length of these bonds. So if you have a high bond order, you have a short length. If you have a high bond order, you have a high strength. And again, we'll just go through here. Obviously, all orbitals of appropriate symmetry contribute to molecular orbitals. We have the sigma orbitals are made of 2s and 2pz on each atom. We have our linear combination that results. Again, when we mix them, we get a superposition of both because we don't know which atomic orbital has which electron. And once we get into, obviously, heteronuclear diatomics, that distribution will be uneven. So anyway, again, we have the 2Bc given this naming scheme here, where this one is higher in energy than this one, so we give it the 2 Gerade, I actually think is what it is, and then un Gerade. I'm probably still pronouncing it wrong. And we know that the sigma bonds have more constructive interference because of their lack of nodes, and therefore contribute more to bonding than our p orbitals. And we also have, yes, the bond discrepancies going down the orbital. As we can see here, the configuration of the relative energies of these bonding orbitals changes as we go down, and that's based off of the relative separation between the energy levels of the 2s and the 2p orbitals, and we can see them change like so. And there's one, and we see that trend here on the periodic table. And I believe I do have another photo somewhere here, and yes, so here we have from oxygen to fluorine, and then here we have from boron to nitrogen. And we will move on from that. Furthermore, we have the energies of bonding and anti-bonding orbitals, and I just wanted to briefly describe that. So we have this energy here for the bonding and then the anti-bonding. As we see, the absolute value of the anti-bonding orbital minus the energy of the 1s is actually greater than that of the bonding minus the energy of the 1s, which essentially tells us that anti-bonding are more anti-bonding than bonding are bonding, which is important because it just basically is explaining the fact that the energy of anti-bonding orbitals are much greater. Furthermore, I just wanted to explain where these values come from. So K is the measure of the interaction between the nuclei and the electron density in the overlap here. So we're looking at this region, and then our nuclei, obviously here and here respectively. And then J is a measure of the interaction between the nucleus and the electrons on the opposite nucleus. So then pictorially, we're just kind of looking at this interaction. And then obviously S is the overlap integral, so we're just integrating over this region to see the extent of which these orbitals overlap. Okay, so extending MO theory, we're looking at heteronuclear diatomic. So now we have to deal with electronegativity. This is the uneven sharing of electrons. So we have two different ways to look at this, the Pauling and the Mulliken. And basically, this is kind of describing the idea that some atoms have higher electron affinity, and therefore they are more stable, having higher amounts of electron density surrounding them. And we essentially make up this linear combination where we have these two constants, which essentially tell us how they contribute to the bond. So essentially we get the probability of finding an electron near the atomic orbital of the wave function A, which is describing obviously the A atomic orbital, and then the probability of finding an electron is proportional to obviously the square modulus of this constant here. And obviously we have the lower energy atomic orbital has the larger contribution to the bonding MO, and the higher energy has the larger contribution to the anti-molecular orbital. And then finding the coefficients, we use an arbitrary wave function and then vary the parameters until lowest energy is achieved, but we never bring the hypothetical energy lower than the actual energy. So this involves quite a bit of painful calculations using determinants and whatnot, and we normalize the wave function right off the bat. I believe this is called the variation principle. The main idea is that we essentially take an arbitrary wave function and we vary the parameters in order to find the values of C and A, and we vary them until we get the lowest possible energy. And this has a little bit of linear algebra in there, and we basically simplify this down to a secular equation and then a secular determinant, and then we determine the coefficients by attaining the values for energy from the determinant, and then we substitute the value from the secular determinant into the secular equation, which gives us a ratio of coefficients that we can use to solve to get the values of the coefficients. And the features here, if we look at extreme ionic cases, we can approximate with an intermediate value, which is Mulliken's definition of electronegativity. We'd really only want to do this if we're lacking data and we don't have enough information to describe it otherwise, or just solve the parameters initially. I think there's a picture here. So yeah, we're looking at the two extreme cases, right, of the ionic cases, and we're taking the energy there in the middle. Other features of the solutions, we have the fact that alpha and alpha B and alpha A are the energies of the electron when it occupies a given atomic orbital, and we see that if we do the overlap approximation, we see that this value is kind of important and comes up in both linear combinations, and we see that the absolute value of alpha A minus alpha B is the energy difference between interacting atomic orbital, pardon me. We see that as the energy difference between interacting atomic orbitals increases, the bonding and anti-bonding effects decrease. So we want atomic orbitals with similar energy if we want the strongest bonding and anti-bonding effects. And then furthermore, there's just a few other things for polyatomic molecules. Again, we're just summing up all these constants in the wave function, very, very much similar to the heteronuclear diatomic, but now we've got way more shapes, and this makes the math much more difficult, and essentially we have to use software for these calculations. The book does talk about ethene, where we make a ton of approximations in order to do some math on these things by hand. Again, I have another picture of just how drastically these approximations do affect the math somewhere in here. But essentially what we're doing here is we are taking a very difficult mathematical problem, and we're setting all the carbons to be equal. We're making the sigma bonds fixed, and then we're just looking at the overlap of the pi bonds and of the bonding orbitals and the anti-bonding orbitals for just the pi electrons, and we're setting the overlap integral equal to 0, and then we are setting all of the resonance integrals equal to 0 except for the neighbors. And really what we get out of this is that we have a HOMO and a LUMO, which obviously is the highest occupied molecular orbital, so we'll draw in some electrons there, and then the lowest occupied molecular orbital, these are called the frontier orbitals, and they really have the most to do with the actual chemical reactions that these guys can come in actually facilitate. So furthermore, we have a lot of determinants here to do these calculations, which I don't really see the point of getting into, but we have the Hamiltonian determinant, the overlap determinant, and then also the constants or the coefficient determinant. And we combine those to eventually give ourselves a Hamiltonian with a constant so we can get an eigenvalue. And furthermore, this just tells us a little bit more about the importance of delocalization of energy. We compare butadiene and ethene, and we see that butadiene is lower in energy, and furthermore, we see that our benzene is even lower in energy due to this electron delocalization, which just means that the electrons are very free to move throughout the molecule, and their orbitals become very massive, and that allows for less repulsion and more spreading of charge, so the energy is ultimately lowered. So yeah, I think right there, that'll probably summarize all of the topics that we talked about in regard to MO theory. So thank you very much. I appreciate your time.